Okay, so our next speaker is Johan Henriksson, and he's going to tell us about holographic duality from Howe duality.
Thank you very much, and thank you for giving me the opportunity to present my research. So it was actually quite difficult to prepare this talk because it involves many different topics across physics and mathematics, which each would merit a talk on their own, and I have 20 minutes. But I'll do my best. So this is based on some work we did with Brian McPeak and Anatoly Demarsky from earlier this year, which has the same name as the title of my talk. So let me begin by explaining the context a bit, which is this idea of holography by averaging. It has been motivated by considering the so-called factorization puzzle in holography. In particular, if you have non-zero contributions from bulk wormhole solutions or bulk wormhole saddles in a holographic setup, this can be reconciled in holography if instead of a single boundary theory, you have an ensemble average of a boundary theories. So it's important to exhibit explicit instances of this setup and understand better why they work. So one case where everything works out very nicely is the Norine ensemble considered by these authors. Here one integrates over a continuous Norine moduli space with a homological metric, and this integral gives as the answer a real analytic Eisenstein series divided by some universal denominator. And this right-hand side in turn is a sum over modular images of a certain seed, which happens to be the vacuum character of u1 to the n times u1 to the n symmetry. And in fact, this equation follows from some underlying mathematical identity known as the Siegel-Weil formula. So what I want to talk about today is another instance, which is based on what we call code CFTs. I'll explain that in detail later. So here we have a discrete ensemble. We just have a finite list of CFTs, and we sum over them with equal weights. And on the right-hand side, we also have a sum over modular images. Here, a finite sum over modular images. And like in the previous case, we're also able to relate this to some underlying mathematics. In this case, something called Howe duality. So this will be the central point of my talk. And this Howe duality is actually, in a way, a generalization of the Siegel-Weil formula. So first, I want to introduce error-correcting codes. So an error-correcting code is a collection of binary vectors, or more generally vectors mod p. So here is an instance of 16 vectors which are chosen in such a way that the minimal distance between each of these vectors is 4. And this can be used to send a message. Say you have 16 different messages to send, and if one of these bits get flipped, under transmitting this message over a noisy channel, you can still recover the message by going back to the closest vector that you sent. So error-correcting codes have been studied by mathematicians since the 1950s and have very deep connections. One is that they can be used in practice. For instance, the Voyager mission used a code similar to this one to send messages back to Earth. Mathematicians have listed and classified these theories, and in particular look for good codes which have large distances between these vectors. And this is in a sense similar to a large gap on the CFT side. For us, two aspects will be important. One is that codes can be used to construct 2D CFTs, as first shown by these authors. And this is by a lattice construction. So this gives 2D lattice CFTs. And if you start from this particular code here, you actually get the E8 chiral CFT. Second point is that codes come in natural ensembles. So it's possible to list all codes with a certain length and a certain property, and compute properties of this ensemble. In particular, the average over codes have been known since the 1970s. So today I want to consider codes over Fp, the field with p elements. So we define a code to be a collection of vectors inside Fp to the 2n. So I consider even length codes. And such a code defines a Lorentzian lattice if we embed Fp to the 2n inside Z to the 2n as the unit cell. And this lattice can in turn be used as a momentum lattice for a corresponding Norine CFT. And these will be our code CFTs, so they are discrete points inside an Orion moduli space. Associated to a code is a polynomial called the enumerator polynomial, which is just a sum over formal basis vectors indexed by the vectors in the code. So this is a vector in a finite dimensional Hilbert space of dimension p to the 2n. This is directly related to the CFT partition function. If we replace these formal basis vectors with functions of the moduli and also some fugacities. This particular function, the precise form is not important for what will follow, was actually found earlier, and it agrees with what was called non-holomorphic conformal blocks of abelian Chern-Simons theory. So I mentioned ensembles of codes, and it's possible to write down a formula for how many codes of this class that I consider, which is even self-dual codes, as a function of n and p, where n is the length and p is the prime that we consider. So as you can see from this table, the number of codes grows factorially. And at some point, it becomes impossible to list all the codes. However, for small n and p, we can list all these codes and compute the average enumerator polynomial explicitly. In the simplest case, where we just have n equals 1 and p equals 3, there are 2 codes. Each of them have 3 vectors, so their enumerator polynomial has 3 terms. And we can just compute the average by summing them and divide by 2. So next, I want to show how we can recover this by a holographic computation, which is this idea of summing over modular images. So although these average formulas have been known for a long time, it was only recently that we realized that for different types of codes, we can always write down these code average formulas as a sum over modular images, where the seed is this psi indexed by the 0 vector. So to do this, you need to discuss modular invariance. So the modular invariant over the partition function of the code CFT follows from some identities that were written down on the error correcting code side already very long time ago by McWilliams. In particular, there are 2 identities, one corresponding to modular S and one corresponding to modular T. So for an even self-dual code, their enumerator polynomial is invariant under these 2 identities, which in turn gives modular invariance of the corresponding CFT. So now we can test this idea that we should sum over modular images of the 0 vector. We see that if we act with T, we would introduce phases that all are unit. So in order to get some new, we should sum over unique terms. So to get something new, we need to first act with S, and then the list quickly exhausts, and we just have 4 terms in total. If we expand all of these terms out, we get these 4 lines. And if you consider, for instance, psi 1, 1 here, it appears with 3 different phases, and all these phases cancels. So what they have in the end is psi 0, 0, and these 4 terms we had in the previous slide. So this is just the average of these 2 codes. This is the only case that can fit in half a slide like this, but we have tested this in many low-lying values of NP. And we can also go to higher genus and compute higher genus averages. For instance, there are 40 terms at genus 2. So by explicit computation, we can check this identity ensemble average equals sum over modular images, case by case in NP. But we would like to have a proof of this formula in generality. Luckily, we're thanks to the finiteness of all ingredients here, we're in quite a good situation to do this. Firstly, everything takes place inside a finite dimensional vector space. At genus G, this just has dimension p to the 2gn. Then there are 2 finite groups that acts on this vector space. One is the group of modular transformations, here projected onto the field with p elements, so this is a finite group. And the second one is another group which I haven't discussed yet, which is an orthogonal group which acts on the labels of these basis vectors. It has an important property that it acts transitively on the set of codes, meaning that we can reach any other code from a given code by acting with members of this finite orthogonal group. So we can rewrite this an identity we would like to prove in a more symmetric form. On the left-hand side, we have a group average over the orthogonal group, and on the right-hand side, a group average over the symplectic group. Here are some of our entire groups and not unique members by introducing a new normalization constant. So this gives a very simple idea of a proof that if we can show that there is a unique one-dimensional subspace of this Hilbert space invariant under both groups, then these two sides must be proportional. And this is because both sides are invariant under the two groups. One group is obvious because it's a group average, and the other one follows from the seed being invariant of the group not appearing in the sum. So this is where this idea of Howe duality comes into the picture. So Howe duality, or also known as theta correspondence, is a topic in mathematics that explains certain properties of paired representations. So there are two ingredients for this. One is a reductive dual pair, which is a pair of commuting subgroups of a larger group, G. And these two subgroups are mutual centralizers. For us, this will be the symplectic and orthogonal group inside a larger symplectic group. It also concerns a certain representation, omega, which is known as the oscillator representation. And it's a minimal representation of this larger symplectic group. And for us, omega as a vector space will be isomorphic to our genus G Hilbert space. So now the central statement of Howe duality is that if we consider omega as a representation not over the whole bigger group, but as a representation of the product group, it has the structure of a sum of representations of each factor indexed by a joint label. So here rho I are representations of G, and pi I are representations of H. This is similar to Schur-Weil duality, which you might have heard of, in which n tensor products of a vector space is a sum of representations indexed by Young tableau lambda, where we have representations of the permutation group and representations of the general linear group. In the case of two factors, we just have the matrix decomposition in a symmetric and antisymmetric part. So here is the outline of the proof. We like to prove equality of these two group averages, or at least proportionality, because it's easy to fix the normalization constant afterwards. So we consider Howe duality, where one of the factors is this orthogonal group, the other one the modular symplectic group, and the oscillator representation being our Hilbert space. Then we take this central statement and separate out the singlet representation of the two groups, plus a sum over non-invariant terms. This shows immediately there is a one-dimensional vector space invariant under the product group, so it must contain the two sides of this equation 1. Turns out it's not quite this simple, and we needed some precise statements for Howe duality over finite field. Luckily, this could be found in the literature, and in particular, we needed a conjecture from the 90s, which was proven only very recently in the math literature. So far I discussed an explicit instance of holography by averaging coming from the ensemble of error-correcting codes. And we followed this blueprint from the Narayan ensemble and saw that we have an ensemble average equals sum over modular images. Moreover, we proved this equality using Howe duality over finite fields by this idea that we have a unique one-dimensional vector space invariant under a pair of commuting groups. So in my title, there was also the idea of Chern-Simons gravity. So this is what I want to talk about in the remaining time. So Chern-Simons gravity is not an established concept in the literature, but we think that this is a phrase or a formulation that can describe our setup pretty well. So imagine you want to construct something that should be called Chern-Simons gravity. One way to go is the following. We start by level P abelian Chern-Simons theory on some bulk manifold B whose boundary is a Riemann surface, sigma G. And this theory has a Hilbert space which is spanned by all possible charges inserted of Wilson lines on non-contractible cycles, so these green cycles in the picture. this is a topological quantum field theory. It has a global ZP times ZP one-form symmetry carried by these Wilson lines. Now we can make a little bit of a leap and appeal to this conjecture that the theory of quantum gravity should have no global symmetry. So we can try to gauge away this symmetry. In practice, what you need to do when you do this is that you need to look for a maximum non-anomalous subgroup of this symmetry. And this was nicely worked out in the paper by Benini, Coppetti, and Di Pietro. And what you get at the end is that, what you get at the end is you get the sum over vectors in this, or charges in this non-anomalous subgroup. What was realized later by Barbara, Dimarski, and Shapiro was that there is actually a one-to-one relation between such maximum non-anomalous subgroups and even self-dual codes of exactly the type of codes that we consider in this work. So you can actually make a second leap, if you want, and say that there are many such non-anomalous subgroups. So why choose one? Instead, we could average over all such gaugings or all such codes with equal weight. And this would give the left-hand side in our equation, the ensemble average. Now, you could also try to take a more conventional approach to Chern-Simons gravity, which would be to start from the idea that gravity should imply a sum over geometries, or in this case, sum over topologies. We should sum over all bulk topologies B, whose boundary is a certain fixed Riemann surface. Under certain circumstances, we can limit this sum to so-called handle body geometries. In this case, we can reorganize the sum as a sum over modular images of a certain fixed topology, such as the filled multi-torus. And this is a similar idea that was proposed in pure gravity by Maloney and Witten. So we get the sum over modular images of a fixed topology. And this in turn is the contribution from the zero vector in the code. And this gives the right-hand side in our equation. So to summarize, we have seen an explicit instance of holography by averaging, and the equation ensemble average equals sum over modular images. And this ensemble arises naturally by gauging maximal subgroups of ZP times ZP one-form symmetry of abelian Chern-Simons theory. And we have a new interpretation of our equality as a sum over gauging equals a sum over topologies. So if you want, this consists of two different pictures, dual pictures of this putative Chern-Simons gravity. And moreover, we prove this equality in this ensemble using Howe duality over finite fields. So 2 words on outlook. There are actually many different manifestations of this Howe duality. And it would be interesting to bring them all into some unified presentation, and in particular a presentation that's accessible for physicists. One is that they're kind of generalized Siegel-Weil formulas, and we first learned about this connection in this nice paper by Ashwin Kumar et al. There is another connection to quantum information where this oscillator representation is actually a Q-dit Hilbert space, and it inherits certain structure from Howe duality. Moreover, there is this idea of paired representations with joint labels that actually shows up in different places in physics. For instance, in the solutions to the spherical potential problem, which factorizes in a radial solution and an angular solution, where this label L is a joint label. It would also be interesting to use this ensemble and similar ensembles to study other observables in holography by averaging. And here we conjecture that if you want to consider a correlation function of local operators, one should average over all theories which contain this particular local operator. And this is very easy to do in the code ensemble. And this should be matched instead of with some of modular images where the seed is not only the vacuum character, but also the character corresponding to the operator you consider. So this is a conjectural equation. We have tested it in a few cases, but it would be interesting to try this in more generality. So thank you very much for your attention.
Questions? Boris first and then.
Thanks for the very nice talk. So in the context of this narrowing modalized spaces, there are other versions of this Siegel-Weil formula where you don't just average the partition function, but you also include some measure, which is itself an Eisenstein series. And the result also is a sum over modular images. I was wondering whether a similar thing occurs in the context of codes. That is where you would choose a different weight for each of the codes and still nonetheless get the sum over modular images.
Yeah, so that would in a way be, so one way to formulate this Howe duality is that there is some kind of map of representations of one group onto representations of the other group. And so far, I've been studying the map of the singlet and the one group to the singlet of the other group. So we haven't tried this, but here it would be very concrete to say, look at an observable transforming in another representation here, and look what happens under this map as a representation of the other group. And in fact, this mathematics literature tells us more in generally what happens for all these representations, at least in a large class of representations. We haven't studied it, but I think this is probably what you need to do if you want to study these correlators.
I'm wondering, so you've proven that one, I'm here.
Who's speaking? Ah, there, sorry.
You have proven that the ensemble average is proportional to the sort of holographic sum, but you didn't talk about the proportionality factor. So usually in holography, there's not some arbitrary proportionality factor. So I'm wondering whether you can say something about that, if you can compute it from the bulk, or what the meaning of this arbitrary factor is.
So this proportionality factor, we treat in a very trivial way, because you can quite easily keep track on how much this like psi sub 0 vector appears in the two sides. So since two sides are manifestly finite here, we just extract it from there. We don't have any interpretation of it in this case.
It's not like, but holographically from the bulk, you wouldn't have divided, for example, in your example, you had 4 terms and you divided by 1/2.
Yeah.
So you wouldn't have put this factor of 1/2 usually in a bulk.
Yeah, I cheated and put it there from the beginning. You spotted that. Yeah, no, we don't have any explanation of this. Maybe by tracking, there's actually a limit you can take of this ensemble when p goes to infinity, which hasn't been worked out in detail. And by doing that, one could compare the normalization you need to insert here with the normalization in the Narayan ensemble. That would be interesting, but we haven't done it.
So have you also considered what happens if your boundary is a sum of disconnected terms?
Yeah, this is relating back to the idea which I just mentioned in Word in the beginning of wormholes. So the whole point is that if you have say, just 2 tori as the boundary, then if you sum over bulk solutions, they should have disconnected pieces, which have a factorizing CFT partition function, and then some connected pieces. So one thing you can do in these ensembles, you can just, for instance, very explicitly estimate the size of these connected pieces, and they are indeed non-zero. And then you can see what happens to them. For instance, if we go to the limit of large central charge, then you expect that maybe they should be suppressed. And indeed, we found an exponential suppression of these connected contributions.
But is there some, can you write it as some sum over topologies, or something that looks like a sum over topologies connected and disconnected?
Yeah. You can just look at this. I mean, we write it as a sum over modular images, right? And then you can try to interpret each of the sum.
I mean, this is modular. Right now you have 2 modular groups, right? You have a torus and a torus, so they each have a modular.
So you, okay.
But I want to say those are not bulk topologies, right?
So
They're
they're
modulars of disconnected and connected topologies.
I see what you mean. Yeah. Okay. So in this case, you need to do high genus computation, and then the disconnected would be, for instance, if the paired matrix is block diagonal and there are zeros off. Yeah.
Further questions? If not, let's thank our speaker again.